So matter and energy. Do you have a benchmark coming up in a couple days? You have a STAAR test soon after that in May. So this is going to be our review packet that we're going to use for our benchmark and our STAAR test. We used it last year and it was pretty successful with it. So, all right, let's start with matter and energy. Physical properties of matter. My mom plays Roblox till Saturday evening. What a great mom. All right. Mass, magnetism, physical state, relative density. Does it sink or float? T is thermal energy. Does it conduct or insulate heat? Okay. S, solubility. Does it dissolve? And then E, finally, is your electrical conductivity. Does it conduct or insulate electricity? All right. So the other things I want you to focus on for this and maybe write down are your points, right? So boiling point is what? 100 degrees Celsius. All right, freezing. What's the freezing point? 0 degrees Celsius. And then finally, you have melting point. What is the melting point? 0 degrees Celsius. Very good. All right. Let's move on. Conductivity. Conductors and insulators. Conductors allow energy to pass through. Insulators do not allow energy to pass through. That's why there's a stop sign. Angelina gave us icy cola. Thanks, Angelina. I and C. Insulators or conductors. All right, next, changes in matter. In order to go from a solid to a liquid, basically an ice cube, it has to melt. Or maybe chocolate candy left outside all day. Okay? Solid to a liquid, it has to melt. From a liquid to go to a gas, think of the hot running shower, right? The hot shower. All that hot water comes out of the shower and it's fogging up the bathroom. Okay? So in order for that liquid to turn into a gas, it has to be hot, okay? And then it starts evaporating. Now you have all that gas in the bathroom from the shower, and when it hits that cold mirror, what does it do? It forms into condensation, right? And those are the tiny little water droplets you see all over the mirror, which is why you can't see your face when you get out. All right, so that's a gas to a liquid. And then finally, to get that liquid to a solid, you have to freeze it, stick it in the freezer. And it has to get down to what degrees? 0. Yay. Okay. All right. Relative density. Does it sink or float? MoFlow. That was fun. We came up with that. MoFlow. All right. If it's more dense, it's going to be on the floor, right? More flow. MoFlow. All right. Oil, water, and syrup. Hey, guess what? Up in the front of the room, I made the cup just like this. I have oil, which is on top. Or not the cup, but the water bottle in the front of the room. It's all yellow, right? Cooking oil. Then you got water in the center. I turned the water green so you could really see it. And then finally, you've got corn syrup down there. So syrup. More on the floor. So which object has more density? The syrup, because it's on the floor, right? All right. Next, let's talk about solubility. Things that are actually able to be dissolved. Soluble, salt, sugar, honey, and lemon juice. Don't forget the lemon juice. I know y'all forgot it on the warm-up. Insoluble, oil, glass, metal, plastic. Those are things that do not dissolve. Okay. Mixtures and solutions. Mixtures is anything that is a combination of 2 or more substances. Okay. How about Chex Mix? What else? Salads. Okay. And then I challenge you to find one other thing and write it down. All right. An example they gave you here is iron fillings and sand. Can you separate those two easily? Yes. What do you need to use? A magnet. Exactly. All right. We're moving on. Solutions. Solutions, you got to start with a mixture, right? Take that mixture, mix it all up. But then this time, when you mix it up, the physical properties actually do change. Okay. Examples here are salt and water. Right? Salt dissolves in the water. Can you easily separate that? No. What's another example? How about Kool-Aid? Everyone loves Kool-Aid. All right. Well, what else? What about all the ingredients it takes to make ketchup. I love ketchup, actually. Okay. Remember the hand sanitizer? When I tried to read the ingredients off the back, there was like thousands of ingredients, and they're all hard words. So how about hand sanitizer? Tizer. I guess I spelled that right. All right. And again, come up with one more example if you can, which you should be able to, and write it down. All right. Physical properties and mixtures. So here's the thing about mixtures, right? Some ingredients in mixtures, they maintain all their physical properties, just like in the Chex Mix and the salads. But sometimes their physical properties change, like with the Kool-Aid and the ketchup. But when iron fillings are mixed with sand, the iron fillings are still magnetic. What? The same color and the same mass. Wow. On the other hand, when salt is added to the water, the salt size changes, right? Because can you see it no more? Or can you see it anymore? No, you cannot. And the water taste changes too. Ugh. All right, force, motion, and energy. Let's talk about our light. Oh, I told you on our last CVA, light energy kind of our booties, all right? So let's talk about some light energy. All right, first of all, we all know light travels in what kind of line? Straight line, right? It always travels in a straight line. But when it hits an object, it can do a couple different things. It can bounce off, right? And we call that reflection. Or it can actually bend. Now we call that refraction. So let's talk about reflection real quick. Light's going to always bounce when it hits shiny surfaces, such as mirrors. What about lakes? Okay, we had a picture where we all kind of bombed that question, where it had a lake and then a mountain in the background, and you could see the reflection of the mountain in the lake. Pretty cool, huh? That's because that lake is dark colored because it's a lake. And when the surface of it is so smooth, right? There's no ripples in the water, no waves, no nothing. And it's a super shiny because of the way the sun is hitting it. So whenever it hits the sunlight hits the mirror, hits the lake, you can actually see a reflection in there. Okay. And besides lakes, what about some people's sunglasses, right? I have a pair of sunglasses that actually reflect. Okay, you can see yourself in them. Not all sunglasses are like that. Also, what about like when you go to shopping malls or stores and like their windows are so dark and shiny, you can see yourself when you walk by, and you're like, "Hey, that's a window." But how is it a mirror? What? Okay. All right, and then let's talk about refraction. When light actually bends, okay, as it hits, when it goes from like point one place to another, and it like windows, right? And it actually bends. Or water. So when light hits water, cameras, eyeglasses, or telescopes, it actually bends. When it bends, it also makes things look bigger or smaller, depending on what it's hitting. That's why if you take a picture with your camera, you can zoom in and zoom out, right? If you wear eyeglasses, it's because you can't see. So it makes things either bigger or smaller, whatever you need. Definitely water. When the straw in the cup of water looks broken, that's because light is refracting it. And if a person is in the pool, remember I told you that if there's a person in the pool, like if it's me, like, and I'm standing, like half of my body's out of the water and the other half is in, like the top part of me will look like normal size, and then the bottom part that's in the water will look all huge and, like I got a big old booty or something, So that's what happens when light refracts. Yeah, pretty cool. All right, let's talk about uses of energy. Melts, MELTS, right? Mechanical, electrical, light, thermal, sound. Mechanical is anything that requires movement, right? So turbines, a hammer, you smacking on a hammer, you riding a bike, you riding this stuff, riding melts down. That's mechanical energy, okay? All that is just any kind of movement. Electrical, that's your computers, lamps, anything that requires a wire. and a battery source. Electrical, remember, it just has energy running through it from a power source, like a battery or the sun. Let's talk about light energy. Light is light coming from the sun. Solar panels use light energy. Photosynthesis has to use light energy. Okay. Light energy can be produced by TVs. How about some alarm clocks? Can that produce light energy? Absolutely. What else can produce light energy? Computer screens, tablets, phones. Okay, good. Thermal, heat. Thermal is heat. Remember that. So ovens, melting, anything that's thermal, heating up. Okay. What about, again, talk about TVs and computers and tablets and phones. Don't they get hot when you're using them all the time? They sure do. They get warm. All right. Sound. That's just hearing. Okay. Anything that you can hear. Sound energy. And sound is produced by vibrating waves. Okay. Real quick while I'm thinking about it, what travels farther and fastest? Sound energy or light energy? Light energy. All right. Force and motion. Fortnite games for me. Okay, we all came up with that as a class too. Fortnite games for me. Friction, gravity, force, motion. Friction is just a force that works against another motion. Okay. When we did the experiment with the carpet and the sandpaper, okay, the carpet and sandpaper were applying more friction to the item that you were pulling with the spring scale than the smooth table. Gravity is a force that pulls two objects towards each other. Basically, pulls you to the earth, pulls the pen that I dropped in class to the ground. All right. Force is just a push or pull. All right. And then motion is movement. So if I'm pushing this pen, did I cause movement? Did I cause motion? Yes, I did. All right. Let's go jump to circuits real quick. All right. Simple circuit. All right. So let's go back to our circuits. All right. Simple series circuit is just one path, right? Just one path makes it a simple circuit. However, if you have two or more, that's why I put a 2+, then it's a parallel path. Okay. Remember, simple circuit, if you go to Walmart and you buy the cheap Christmas lights and one bulb breaks, the whole set's going to break. Okay. And that's really kind of a stinker especially if you actually hung them up on the house or something and then one bulb breaks and then you got no lights. However, if you would have spent an extra $1, right, you could have got the expensive kind, right? And when one bulb breaks, it's okay. They all still work. So I always say there's, so like I said to my husband, there's always good reasons for spending the extra money. All right, because you kind of you gotta get what you pay for. So whenever we have a simple or parallel circuit as a test question, where do I always want you to start following the energy? I want you to start at the battery, okay? So let's start here and let's flow. Energy, energy, energy flow. Singing the song as we go. Oh and oh. All right, so we come in one side. We got to go out the other side, right? And then what happens when we get to the switch? First of all, do you even need a switch in a circuit? No, you don't need a switch. But we have one. So what should we do? This switch is open right now, I'll tell you that. So this energy cannot go on anymore. And it's kind of just hanging out there. But if Gabriel comes along and he actually closes a switch, thank you, Gabriel. Now we can continue on. Energy, energy, energy. And we're going to go right back to the other side of our battery so that we actually have a complete path. Yay. All right. A closed or complete circuit allows energy to pass through. Hey, this is exciting. Yay, we want that kind. And then an open or incomplete circuit does not allow electricity to flow through it. Boo. Bad kind. All right, so a closed circuit is shown below. All bulbs appear lit. Well, right now they are. We got a switch that's closed. We've got everything appears to be hooked up correctly. So let's talk about this real quick. Let's name this one A, this one B, and this one C. What if the test question says, what can you do to make C not work? Well, this is when we don't want to work. So there's a couple things we could do, but let's just start at our battery because I want to go over Y intersections again. All right, start here. Energy, energy, energy flows. Where it's going, nobody knows. Got to go in one and out the other. Okay. I don't know. Just making up the stupid song as I go. All right, now I'm at a Y intersection, right? Makes a little Y. I can continue to go that way, or I can come down this way. But if our test question says, what can we do to make C not work? Can I cut this wire right here? Absolutely. Because then if my energy tries to come, if the wire's cut, it's got nothing to go anymore. So that's one way to make C not work. But the energy can still go through here, right? Like that, in one side, out the other. Okay, we're back at another Y intersection. Now what? Could I have cut the wire here? Absolutely, because then it would have hit here and then, nope, not going anywhere. But it can continue to still go through this way, okay, into the switch, other side of the switch, and back to the battery. All right, so let's move on. Designing an investigation that tests the effect of force on an object. Example 1, use a spring scale to drag a block on 3 different surfaces to determine if different surfaces affect the amount of force needed to move the block. Well, we kind of did this yesterday, although we didn't do a block per se, but we did pull different random items, and we pulled them on this table, we pulled them on the carpet, and also on the sandpaper, okay? Should you have done it 3 different times each time to make sure you get an accurate reading of the force? Yes, but we didn't because we just didn't have the time. If you pull it on different surfaces, what were the 2 surfaces that provided the most friction? The carpet and the sandpaper, right? Equal friction. How's that? You like that? All right. And we use our spring scale, right? We were dragging them, and we all actually measured out how much newtons it took to pull the item. One thing we didn't do yesterday was a spring launcher. Okay, I don't have a spring launcher, but a spring launcher essentially is just this thing. It has spring in it, obviously. You can push, like you can put like a sphere or like take like a ping pong ball, you know, but actually have like a lot of weight to it. And if you stick it on there and you pull the spring all the way down and you let go, is it going to fly in the air? Yes. Okay. It launches into the air. It's like a launcher, right? That's why it's called a launcher, spring launcher. Anyway, it flies in the air. But what if you did a heavy, like, baseball and you did a ping pong ball? Which one do you think would fly farther in the air? The ping pong ball or the baseball? Actually, it'd be the ping pong ball because it's lighter, so it can go way higher. All right. And then you can measure the distance. All right. Let's move on. Earth science, fossil fuels. Fossil fuels. Con. All right, con is coal, oil, natural gas. All fossil fuels are formed from dead organisms. Okay, something biotic had to live once upon a time. Then it died, right? And then it got buried under a whole bunch of stuff and sediment and stuff. And then a lot of heat and pressure over time came and pressed down on it, right? And then millions of years had to go by. Millions of years. And then finally, you either get coal, oil, or natural gas, depending on where you actually, depending on what died. Okay, so if plants died, right, what did it make? Just plants. It made the coal, so we put plants. And what about the oil and natural gas? What had to die? Do you remember? Marine life. So I'm going to put H2O life. Okay. Marine life had to die. H2O life is what I wrote. And that's thanks to something biotic living once upon a time and dying. We now have coal, oil, natural gas, which are our fossil fuels, which are going away because they take millions of years to replenish. So therefore, they're considered non-renewable. Okay. While I'm thinking of it, what are the renewable resources? Do you remember? Let's write it up here. Silly Baxter wears green hats. All right. Silly Baxter wears green hats. What is the S? Solar. B is bio. W is wind. G is geo, like geothermal, actually. And H is hydro. Okay, hydro means water. All right, let's talk about solar. Solar energy, that's all from the sun. Thank you, sun. Will the sun ever go away? No. If it does, we're all doomed. Bio. Bio just means anything that was alive. Get it? Bio, biotic. Oh, it all comes together, doesn't it? Bio, something that was alive. Bio, I'll just tell you right now, bioenergy is basically when you take corn and you can turn it into gasoline. Yeah, so a lot of people who drive Chevys or GMCs, they actually put that gas in their car that's called E85. That's ethanol, and ethanol is made from corn. All right, wind energy. I think we're all pretty clear that wind energy is obviously renewable because the wind is always around. Okay, as long as there's air, there's wind. Geothermal. Geothermal is something we haven't really talked about too much, but just know that geothermal is any heat that's coming from underground. Because as you go deeper into the ground, does it get warmer and warmer and warmer? Yes. So they actually pump energy, hot, steamy energy from the earth, from deep down in the earth, underneath your houses and buildings and cars, all the ground. And they actually take that and turn it into energy for your homes. Geo means earth, under the earth. And then last, hydro. Hydroelectricity. Hydro is water, and so as long as we have water, we can make electricity. Remember when I told you I went to Vegas and I went to go see the not the Grand Canyon, the Hoover Dam, and they were taking the water, the Colorado River, and it's turning those turbines, and it's making electricity that powers nearly the entire state of Nevada and some of the state of California. So, yay for renewable energy. All right, and if you can't remember, it's Silly Baxter wears green hats. That's I came up with that last year. All right, landforms. Landforms. Speaking of the Grand Canyon and Hoover Dam, let's talk about canyons. Canyons are formed by water, okay, weathering rock and eroding sediments. Water just runs through the same ground all the time, all the time, all the time. And it just wears away the rocks. That's how canyons are formed. Grand Canyon. Grand Canyon. Does anyone remember the name of that river that runs through there? I just said it earlier. Colorado River. All right, deltas. Deltas are fun, right? They look like little veins. That's formed when water deposits sediments at the mouth of a river. So remember we got the flowing river? We talked about this on our question warm-up the other day. And we got a little fish. Let's just talk about this. Little fish, right? And then remember the beaver came and he cut down a tree. Okay. Now the fish, can they swim anymore? No. But that water still has to run. So what does it actually do? It's going to find places in that where that tree is laying in its way, and it's going to find and go around. Okay, that's why deltas make look like veins in your hand. Ooh, yeah. Okay. Sand dunes formed by wind. Wait, how do I get that sand pile to go from here to here? I could blow it, right? Sand dunes are formed by wind. Remember, blow. All right. Let's see. Day and night. Let's talk about day and night. Day and night is caused by Earth spinning on its axis once every 24 hours. Yay. And we call that rotation or revolution. Rotate. Ballerinas rotate. The Earth rotates. Okay. Whenever one side is facing the sun, it's got daytime. When the other side's facing the sun, when the other side is not facing the sun, it is nighttime. And what is it called when the Earth goes around the sun? Revolution. Okay. As I'm walking around the room during your test, am I rotating in the room or am I revolving in the room? I'm revolving. All right. Let's go to this one. Yay, I love this one. The rotation of Earth on its axis causes the apparent movement of the sun across the sky from east to west. So the sun comes up in the east and it sets in the west. If it comes up in the east, this is all AM, right? Morning time. What is right here? When the sun is right there, what time of the day is that? Noon. Okay, and that's when AM turns into PM. And then the sun starts to go working its way to go down, right? And all of this is PM. So if you had a question that says, hey, where would the sun most likely be at 9 a.m.? You would know it would be over here somewhere. What if it said it was at 3 p.m.? It'd be over here somewhere. Okay? When the sun hits right up directly above the sky at noon, you know it went from AM to PM. All right. I hope if you have any questions on that, let me know. All right. Sedimentary rock formation. Yay! We came up with we eat delicious candy canes. Wed CC, rocks, weathering. Rocks are broken down into tiny pieces called sediments. And then those sediments are eventually carried away to another place. When they finally land in their new place, okay, that's called deposition. And then, like sometime later, another piece just happens to fall on top of it. And then another piece, and then another piece, and another piece. And all that is just compressing down, right? So it's pressing down, because that little piece down here is getting so, like, squished, right? Remember we talked about in your family, have you ever had a human sedimentary rock, right? Where you're laying on the ground or you're laying on the couch or the bed, and then someone has to come and just lay on top of you, and you're like, oh gosh, no. And then someone else lays on top of them, and then someone else comes on top of them. In the meantime, you're like, I'm getting squished, I can't breathe. Because that's all compaction. Yeah, they were all compacting on you. What would happen now if you came and you throw some water in there? You would all stick together like glue. That's cementation. Remember, the water acts like glue. If you took your science journal and you dumped it in a puddle of water, would the pages be stuck together? Yes, not because the puddle of water was made of glue, but because it's water, and water just somehow can make things stick together. Water's pretty fascinating. So, Wed CC, once all that compaction and cementation happens, then you have a whole brand new rock. Guys, I'm thinking of something right now. Please do not confuse this with this. Nothing that was once alive ever has to die to make rock. Rock is rock. Nothing ever alive has to die to make rock. Nothing alive ever has to die to become a rock. I mean, how awful to say you gave your life away to be a rock. Oh, that's horrible. Who wants to say that? No one. But something that was once alive has to die to turn into an awesome fossil fuel. Yeah. And that's what it should be. I mean, like, you should totally not have to die to turn into a rock. You should totally die and then get to, like, slowly over millions of years turn into something that people can actually use. Pretty cool, huh? Think about it. Something has to die that had energy in it. And then that energy is transformed into coal, oil, or natural gas, which is the energy that's needed to make cars go boom, boom, or to make houses heat up, or to cook your food. All that's energy. Energy just has to transfer. When a rock dies, does rock have energy in it? No, because nothing that was once alive had to die. Pretty cool, huh? All right, moving on. Water cycle. Water cycle. All right, let's start the water cycle. What has to heat everything up and make everything work? The sun. He's so important. All right. He heats up all this water down here. And because of that, evaporation occurs. All right. As it occurs, think of the shower. Go back to the shower scene, right? You got your shower on. It's all nice and hot, okay, and all that steam because it's like super hot, right? It's coming out of the shower. Are you like getting the hot water and are you throwing it on the mirror? No, if you did, I'm sure your mom would be pretty upset about that. But you are probably got some super hot water going on and you're all nice and toasty and warm in your shower. And then when it's time to get out, you pull back the shower curtain and you see the mirror. Oh, but you can't see yourself in the mirror. Why? Because it's got all that moisture on it, that water. But how did it get there? Well, funny thing, that water that was so hot, it evaporated. And when it hit that cold mirror, it quickly turns back into water. Okay. And that is called condensation. And that's all your little clouds. That's all it is. Clouds are little tiny drops of water. Okay. Because when that hot evaporation hits the air up high, the air is colder than it is on Earth. Okay. It turns back into water droplets. And then when the clouds get so heavy they can't handle anymore, they give up and precipitation comes out. Okay. And precipitation can be rain, snow, sleet, hail. And then that precipitation comes back on Earth. And of course, thanks to gravity. Yay. Hello, gravity. Yay. Thanks to gravity, all the water runs downhill and eventually back into your lakes, streams, and ponds where it can get warm again and go back up. All right. Order of our planets. How do we remember our planets? My very excellent or educated, whatever you want to say. My very something mother just served us nachos. She's so sweet for that. The only tricky thing about remembering the planets and their order is you've got two M's. Do you remember what I said that helps you remember which M is closest to the sun? Sun. All right. I told you that when you move into a new neighborhood, right? Are you going to go meet your next door neighbor first, or are you going to go all the way down the street and meet some other random neighbor? Most people meet their next door neighbor first, okay? And so same thing with us on Earth. Are we exploring Mercury right now, or are we exploring Mars? Do we have all these cool Mercury missions, or do we have Mars missions right now? We have Mars because we're going to go explore our next door neighbor before we ever go far down the street. Make sense? So it's Mercury, Venus, Earth, Mars, because we're next door neighbors. We're buddies. Whatever you can come up with that helps you remember that the second M is Mars. Use it. All right, last page. I know this is really long. I'm sorry. Photosynthesis. Plants produce a type of sugar using carbon dioxide, water, and sunlight. How cool is that, right? All right, so your sunlight comes in. It's going to hit this plant. This sunlight plus the carbon dioxide, that's that stuff you breathe out. Okay. But those two may come on into the plant because the plant pulls it in. And now he's got the water that's on the ground and he's making his photosynthesis. He's making his energy, his food, right? And then as a result, the plants give back oxygen to us. So nice of him. It really is. Like, Mr. Plant, that's so nice of you. Ecosystems. Don't worry about this glucose. Ecosystems. Yay, ecosystems are so fun. Ecosystems is just straight up the interaction between all non-living, which we call abiotic, and living, biotic, things in an environment. So, again, if you're biotic, you need to depend on abiotic things to stay alive. Abiotic things are like air, sun, water, soil. All those things are non-living, okay? But if you're biotic, if you're living, you have to have those things to help keep you alive. I mean, you just do. All right, so let's talk about our food web. Food web. The transfer of energy from the sun. Wait, we don't have a sun. We need a sun. All right. The transfer of energy from the sun to producers. So that would be that guy, right? Consumers and decomposers can be represented using a food web. The arrows show the direction energy moves. So where the arrow goes, the energy flows. All right. Y'all actually done really well on this week. I'm really proud of y'all. All right. So now let's talk some types of organisms. Producers. Producers is any organism that makes energy using sunlight from the sun. So that would be your plants. Here, they give you some examples. Sunflowers, grass, apples, apple trees, phytoplankton, and maple trees, and any plants, okay? All right, then you've got the consumer. So this is the guy that comes along and he's going to eat on those things. He must eat to get energy, right? You have to eat to have energy. And to actually put something in your mouth. Tigers, humans, bees, rabbits, hummingbirds, and goldfish. Oh my. And then last you have decomposers. And decomposers are any living thing that feeds on something dead and then breaks it down and puts it back in the earth. Basically, bacteria, mold, mushrooms, and earthworms. Well, how can an earthworm return energy back to the earth? Well, he's going to go eat on something dead, and then he's going to process it in his body and poop it out, and then it's going to go back into the soil, and it's going to help take that energy, and it's going to turn into more energy, okay? All right, traits and behaviors. These are two right here. These two things we have not talked about in class, so if you miss these questions on the benchmark, please don't freak out. We still have to learn these things before our STAAR test, so we will. So let's talk about traits and behaviors. Inherited traits, anything that's passed on through genes from parent to child. So anything you're born with. I really love to, when I talk about this, I like to play that song, Baby, I Was Born This Way, right? By, what's her name? Lady Gaga. All right, so if you're born this way, then it's a trait. If you're born with blonde hair, blue eyes, if you're born with 6 toes on your right foot, okay, that's not a learned behavior. That is a trait. That is something you got from a family member. Hey, mom, thanks for 6 toes on my right foot. I look rad. All right, so also traits. What if as you come out of mama, you cry right away? You take your first breath of air, you cry. Do you think that's a trait or a behavior? Did you have to learn to do that? No, it's a trait. You had to learn. You didn't have to learn to cry. Everybody comes out crying. Everybody's like, no, I don't want to come out. It's all cold out here. But learned behaviors now, that's something you actually learn to do. It's kind of in the name, right? Riding a bike. An animal learning to sit, roll over, play dead. Those are all learned tricks. What about you right now writing notes? Learned behavior or inherited? It's learned because you had to learn how to write at some point. You had to learn how to walk, how to sit, how to feed yourself, how to change your clothes. You had to learn how to do that. Okay? And then last, I want to talk about structures and functions. I'm going to just hit this real fast. Organisms need food for energy. Do you agree with that? Yes. Okay. Do they need water, space to move or grow? Yes. Do organisms need protection from being eaten? Yes. Do organisms need to pass on their genes to their babies? Absolutely. So physical structures now help plants and animals survive in their environments. So different things that you're born with, or whatever you are, if you're a plant or an animal or a human, there's different things that you are born with that help keep you alive. In this picture, it's a cactus, and it says spines on a cactus in a dry desert prevent water loss. So these spines, the little prickly needles, they actually help keep the cactus to keep the water in. Some we talk about plants have that transpiration where the water evaporates from the plants. Not the cactuses, because the spines, they keep the water in. A penguin's wings are shaped like flippers to make swimming easier. Okay, that would be kind of bad if he didn't have those, because then he wouldn't be able to swim, and penguins swim. A polar bear lives in the Arctic. It's cold there. Why do you think his fur is so thick? It's to keep him warm and keep him alive. So, all right, well, this pretty much concludes our review. Good luck on your test. Review. Watch this video. Study your review. Study your review. Study your review. Study your review. And you'll be fine, guys. You'll do great. I believe in you. All right. Ciao.